Okay, 9.2 is all about possibility trees and the multiplication rule. So we have three things to do in this section. The first is to go over the multiplication rule. Multiplication rule. The second is to then immediately look at the failures of the multiplication rule. Multiplication, we're going to have to squeeze this in because I write too big. Wow, that looks terrible. Let's just rewrite it. Multiplication rule. And finally, we're going to talk about permutations. So, the multiplication rule. And I promise this will be the last time we have to write this in this section. Now that we've written it 3 times, 4 times very quickly here. So if an operation has k steps to be completed, and the first step can be done in n sub 1 number of ways. The second step can be done in n sub 2 number of ways. And this is going to get repeated over and over and over until we get to the kth step. And this can be done in n sub k number of ways. Then the entire operation can be done in n1 times n2 times ... n sub k, or the repeated product from I equals 1 to k of n sub I ways. So in other words, if you have a multi-step process and each step has a different number of ways that you can do it, to figure out the total possible number of ways you can do the entire operation, you multiply every single step's number of ways that they can be done. This is the multiplication rule. And this is the basis for permutations, combinations, and combinations and factorials. It's also something that we do all the time. So we're going to do a couple little examples here about combinations, and let's start with how many total Social Security numbers can be made. So our Social Security numbers: 23-12-1234. So we have to choose something for A, B, C, D, E, F, G, H, and I. And so all of our social security number digits need to be anything from 0 to 9. So A, you can think of as X, which lives in 0 to 9. B, which equals Y, lives in 0 to 9, and so on. So we know from the last section, the counting integers, we have 10 total integers here. So we have 10 choices per digit. And we have 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 9. We have 9. So we have 10 to the 9th. So that's how many total choices there are. This is simply 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 billion. So there are 10 billion total different Social Security numbers that can be made, which means at some point, the U.S. government will run out of Social Security numbers. Now, we know that this is actually closer than what you think because we don't reuse Social Security numbers. So we have, however many billion people live in the U.S. right now or have ever lived in the U.S. that have been citizens, gotten a Social Security number. So this number will eventually get hit, and as populations increase, this will get hit sooner than you would think. But it does mean it's finite. Now, if you're wondering, well, what would they do if they get that? Well, they'll probably just add a digit, because now instead of 10 billion, there's 100 billion different combinations. They can reuse all of the ones that they did before, hopefully a long time ago with a different digit. But it does add an extra term. Now, they probably wouldn't do this just adding it at the end. They'd probably add it in the middle or add 1 to each of these, and you'd have 4, 3, 5 in your digits. But that's not the point. Right? The point is that this is a finite rule, and that this is how we can apply the multiplication rule. So now let's talk about something a little bit closer home. How many PIN codes exist if A, only 4 digit numbers, are allowed, and B, 4 digit numbers / letters, and we're going to say capitals only on those letters. Are allowed. So I'd like you to pause the video here and try this one out on yourself and see what you come up with. So I'm going to walk through the answer now. So most banks use 4-digit PIN codes, and if we look at how many there are, again, our numbers can be anything from 0 to 9. So we have 10 choices for this one, 10 choices for this one, 10 choices for this one, and 10 choices for this one, or for a nice grand total of 10,000. Now in San Diego alone, we have a couple million people. If only half of those, let's say only 1 million people, have bank accounts that use PIN codes of 4 digits, that means at least 100 people share the same PIN code that you use for your bank. Which is a scary thought. And now think about across the US how many people are. There's probably 1,000 or more different people that use the exact same PIN code as you, because there's only so many that we can choose from. So what a lot of banks have been going to is allowing PIN codes One, they increase it. I've seen some for 6 digits, which helps. That gives you a million different options, but still that's not very many. You can still reuse, and they will get reused. And the other thing is what we're looking at in Part B is where they allow capital letters. Now some do a combination. They do 6 digits, numbers, and letters. We're just going to do 4 to see how that improves security. So now if we allow, I can count 4 digits, and we can have any of the 10 numbers, 0 to 9, and any of the capital letters, A to Z. That's 36 choices for each option. And that gives us 1,679,616. Well, that's a lot better. So now if we just think about San Diego has a couple million people, the chances that someone are using the exact same PIN code is better, or is not as likely as if you're only a 4-digit number. It also means that it's really easy if someone was to be able to write software to check PIN codes to crack this version versus this version. The other thing to consider is we don't use certain PIN codes. They don't even allow us. So you're probably thinking to yourself, yeah, there's 10,000 here and there's 1.6 million, almost 1.7 million, but let's focus on this 10,000 and why this is such a bad system. Have you ever heard of someone using a PIN code 0000? Because that's allowed in our combination here, but we wouldn't do that. We also wouldn't allow 111, 222, 333, 444, because those are too easy to just check. You can check all 10 of those really fast. And there's others. They say don't use birth dates, don't use specific dates like your anniversary, because those are easy to guess if people have your information. So for any one person, if we're just focusing on the 10,000 possibilities, you're probably not actually looking at 10,000 possibilities. And we won't even get into things like irrational things, like if you have triskaidekaphobia, which is fear of the number 13, you're definitely not choosing 1313. But this at least makes it more secure because there's more options. And we can do the same thing and kind of look at what's happening in that. So, like I said, we don't use things like 1111. So let's repeat this. Repeat these examples. Without repetition. Extra blurry today. So for part A, that means that once we choose our first choice, we do have 10 options, 0 to 9, but whatever number is chosen, we no longer have that option for the rest. So now there's 9 choices here, there's 8 choices here, and there's 7 choices here. And so this limits you down to only 6,480. And I'm not sure if a lot of banks do this where they don't allow repeating digits, but you can see there's even less choices now. And again, you're going to avoid things like your birth date. You're going to avoid things like your anniversary. So it's not actually 6,480 options because you don't want to use those things that have meaning to you, or at least they advise you not to. And for part B, we do have 36 choices, but then we only have 35, and then 34, and then 33. And so there's 1,413,720, which still looks like a lot, but remember that's over 250,000 combinations that we've just eliminated by this one little requirement. So you can adjust and increase security, but it also makes it harder because if your bank is storing your PIN number, it has to store all of these combinations and make sure that they're all possible. So there's a lot more computing power behind this for the more options. So now let's talk about, we've seen the multiplication rule and how it works. Let's talk about where it fails. And it fails more often than you might think. It fails to actually get the right number of combinations. So let's say 4 people are running for 3 positions. If person 1 cannot be A, so I'm going to name the positions A, B, and C. Sneak that in there right there. So if person 1 cannot be A, and only persons 2 and 3 can be C, how many combinations of people and positions are there? So if you ask someone off the street this exact question, a lot of times they think, okay, I have job A can only be filled by person 2, 3, or 4 because person 1 cannot be job A. So that means for job A, B, and C, I only have 3 options. For job B, I have no restrictions, so I have 3 options because someone's already picked from job A. And from part C, only 2 and 3 can be there, so I have 2 choices. So 3 times 3 times 2, that gives me 18. Well, this is wrong. Very, very wrong. And to see why, we have to use a possibility tree. And so we don't typically set up possibility trees for more general combinations like this, but this one's very hyper-specific. We have 4 people, 3 positions, and then we have some requirements. Person 1 can't be in A, and only persons 2 and 3 can be C. So if we start our selection process, we don't need to do the whole tree to see why this 18 is wrong. So we have job A, we have job B, and we have job C. So our first combination, number 1 can't be job A. Person 1 can't be in job A, so we pick person 2. Well, then we get to B, there are 2 choices, and there are 3 choices here. When we get to B, since person 2 is chosen, person 1 could be chosen again, and person 4 could be chosen again. Now, if you're wondering why only these 2, why not person 3? Well, our requirement is that only persons 2 and 3 can be in job C. So that means in both of these cases, we are shoehorned in from our first choice to what our second choice is. So there's not actually going to be 18 because this only is 2 options. Same thing if we choose 3 here. This gives us, we can be 1 or 4 because here, this has to be 2 and 2, which is only 2 choices. And then if we choose 4, we can have 1 here, and then we could be 2 or 3. We could have 2 here, and then this has to be 3. Make these lines a little more obvious where they're coming from. And then our last choice that we could make if 4 fills position A is if 3 is here, and then the only choice is 2. So we have 2 choices here, then 1, then 1. So we can see we only have 2, 4, 6, 8 options of how these 4 people can fill these 3 jobs. So in the homework, you're going to have some problems like this where the multiplication rule just isn't going to work. And you can almost always identify when this multiplication rule won't work because your situation is going to be complex. It's going to have multiple requirements and very specific, subtle requirements. Person 1 can't be in job A. Only persons 2 and 3 can be in job C. Those kinds of things. When we're talking about the multiplication rule in general, though, we're almost always talking about permutations. So a permutation is an operation on a set that gives the different ways all elements can be ordered. Now, we've been doing permutations. You've been doing permutations basically all your life. Have 7 things. How many groups of 6 can you make? How many groups of 3 can you make? That kind of stuff. So let's look at a quick little example to remind ourselves. So find all permutations of the set A, B, C. In other words, how many ways can we organize a 3-element set? Well, we can have the standard ABC, we can have ACB, we can have BAC, we can have BCA, we can have CAB, and we can have CBA. So 6 total. Now this is fine when we have a small set like this, 3 elements, 4 elements, even 5 elements. 5 elements, not so much. But 3 or 4, especially 2, you can find your permutations by hand like this, and it's not too difficult, not too tedious. But the problem is when we start getting larger, if you have, just our class, 36 people, how many permutations of 36 are there? There's a whole heck of a lot. So for any integer, n greater than or equal to 1, the number of total permutations of a set with n elements is always, we'll put it here, n factorial. So remember we introduced factorial. Did we introduce factorial? Can't remember. My classes are starting to bleed together, I guess. But factorial is a counting principle. It has to do with counting up, in this case, permutations, and that's what it does. It counts the permutations. And so the reason why in that example with the jobs, it's not permutations is because we are doing a combination, but a more complex combination. And there's an actual mathematical construct called combination that we'll be talking about in a later section. So for now, I'd just like you to try we'll work through a couple of these problems. together. So how many ways can you arrange the letters of computer? And then we'll do computer, and we'll give a restriction that O must follow C. So the first one is just a straight permutation. We have 8 letters in computer, C-O-M-P-U-T-E-R. That means that there's going to be 8 factorial. So you can think of this as a set of 8 elements, and we're rearranging them with no restrictions. So this is 8 factorial, or 40,320 different ways. Obviously, we're not going to write all these by hand. It would take forever. And that one's pretty simple. Most people understand that. Now, part B is where we get a little bit complicated. And the way that we think about this is, since O must always follow C, wherever C lands, your next digit, so we're rearranging 1, 2, 3, 4, 5, 6, 7, 8, 8 digits. If C lands here in our choices, then O has to come here. If C lands here, then O has to come here. So it's not that we have however many choices would be here or here and then another choice. This is no longer a choice for us. There's only one way. So the way that we think about this is consider C and O as one letter. So we're essentially combining two digits into one, because these always have to come after each other. And then we're not permuting 8 elements, we're permuting 7 elements, because C and O always come in that order. So we're really doing 7 factorial, which is only 5,040. So this is the way you want to be thinking about it. There's going to be some homework problems that require you to permute letters and permute different sets, and they're going to have restrictions like this. So if you have a very specific thing that has to come right after or right before, you don't really have an option, because once one of those letters is selected, the next letter or next element has to be something specific. So it's not like a number here, this becomes a 1. And if we're multiplying by 1, we're not changing the number of combinations or number of permutations. And so we can just think of it as one whole letter and just make it 7 factorial instead of 8 factorial. So when we're talking about sets, we don't always just do straight permutations, because it's not interesting. You have a big set, you just do its size factorial and factorial. So what we often typically look at is R permutations. R permutations. And in R permutation, permutation of a set of n elements is an ordering of 1 less than or equal to r less than or equal to n of those elements. And so essentially what we're doing is we are taking r things from the set of n and putting them in an order. And so we have some notation for that. So the notation for an R permutation is P of nr equals n factorial over n minus r factorial. Now, we actually have the ability to prove this, and I believe the proof is in the book as well, but you can give it a shot. Try proving this with induction. And you can try that out and check your work. But this is what an R permutation is. So we're just going to walk through a couple examples and then a little proof that uses R permutation. So the first is just some evaluations. And we're going to do the number of orderings of any two integers from 1 to 5 to start. So we are doing the permutations of 5 with 2 choices. And so our formula is just 5 factorial over 5 minus 2 factorial. Now this one's small enough, but the way that we simplify this is going to set us up nicely for the next part of the chapter. So the way that you want to take care of factorials, in case you're rusty, is leave the factorial in its factorial notation until you have just factorials on the top and the bottom, and then split your largest factorial on top until you see the largest factorial you see in the bottom. Those then cancel, and we have 20 as our answer here. So if you're up to speed, you probably did factorials at some point in another class, algebra maybe, pre-calculus, then great. But for those of you who haven't seen factorials in a while, a little rusty, this is the way that we want to be reducing them, is always try and eliminate all the factorials from the bottom first. So in part B, how many 4 permutations of 7 elements are there? In other words, how many ways can we arrange 4 elements out of a total of 7? So we are permuting P of 7 comma 4, 7 factorial over 7 minus 4 factorial, 7 factorial over 3 factorial. Split our 7 factorial into 7 times 6 times 5 times 4 times 3 factorial over 3 factorial, and those go away. And then 7 times 6 times 5 times 4, which is 840. So there are 840 different 4 permutations from a set of 7 elements. So there'll be some problems in the homework to have you get used to this. We're going to be doing a lot with factorials and permutations and simplifying, so we want to be up to speed on factorial simplification, make sure we're not too rusty. The last thing I want to do that will end this section and this video is just a little proof. And proof using some factorial stuff, and specifically our R permutations. Our R permutations. So we're going to prove for all n greater than or equal to 2, n is an integer, that P of n and 2 plus P of n and 1 equals n squared. So because we're doing n factorial stuff and a lot of work, our usual instinct is to jump to, let's use induction. In fact, I even said you can prove the R permutation rule using induction. But some of these proofs, and a good amount of these proofs, are not going to need induction. They're just going to be constructive proofs. So we're going to let n be an integer such that n is greater than or equal to 2. Then p choose n comma 2 is n factorial over n minus 2 factorial. P choose n, not p choose, p of n comma 1 is n factorial over n minus 1 factorial. So if we add these, p of n comma 2 plus p of n comma 1, this is n factorial over n minus 1 factorial plus n factorial over n minus 2 factorial. Well, n minus 1 factorial is n minus 1 times n minus 2 factorial with n factorial on top. So all I need is an n factorial times n minus 1 over n minus 1 times n minus 2 factorial. And so this gives us n factorial plus n factorial times n minus 1. Both of these two things collapse back to n minus 1 factorial. And then we have n factorial times 1 plus n minus 1, which is just n. So this equals over n minus 1 factorial, of course. So this is just n factorial times n over n minus 1 factorial. And now we use our standard factorial simplification techniques. Try and eliminate this from the top. So n factorial is n times n minus 1 factorial, and then still times n over n minus 1 factorial. Well, those go away. N times n is n squared. And that's our proof. It's a simple constructive proof. So I show you this because a lot of the properties you're going to prove are just constructive proofs, but you want to make sure that you're not jumping to induction immediately. Some of them will need induction, so you don't think that none of them are going to use induction, but also keep an eye out when you can just do it constructively. And with that will be the end of 9.2.